Oh, good.
Yeah, can you hear me okay?
Can hear you fine. Nice to see you.
Nice to meet you. Can you see me as well? I'm trying to figure this out here
You
real
you
quick.
you look fantastic. Actually, you're doing great.
Thanks.
So at the moment we have. Well, I noticed Jason is joining us. We have Tom Mason and Jim Fisk, who are part of the Gravity Power team, and then we have Mark and Bryant Beeler, who are Gravity Power shareholders, and I expect some others to be joining as we get closer.
Brilliant. Let me try and share my screen just to make sure we got the logistics right here. All right, give me one sec.
Mhm.
How's that looking?
That's you probably want to go to slideshow mode, but I can see the PowerPoint window.
All right, okay. How about that?
Perfect.
All right. I don't usually use Zoom, so you'll have to bear with me here while I try and figure things out.
Yeah, we'll be patient.
All right. So are you seeing the sidebar here as well?
I'm seeing a slide bar with messages on my screen. I don't know if everybody else sees that. What? Oh, you know what? You may be. Sometimes Zoom will give you a different screen from what it shows to everybody else, so that you have more insight into what's going on. But what we're seeing here is your PowerPoint window.
Right.
It is dropped out of slideshow mode and it's just back in editing PowerPoint editing mode. And
Yeah.
then across the top, we see the people attending.
All right. Let me try that one more time. Looking. There we go. Much better, right?
Yeah, that's perfect. Why don't we give late arrivals a couple more minutes and then we'll get going.
You think we've got about an hour for this one? Is that right? About 45 minutes and 50 minutes for
That's what we have
questions?
scheduled. Yeah, if that works for you.
Yeah, well, that's fine for me. Perfect.
Great. I think Jag, a lot of the people, are you still there, Jag? Yeah, there you are.
Yeah. Okay. Yeah.
I think a lot of the people were unable to make this time because it's a school day here.
Yeah.
And so if you don't mind, I'm recording it and I'll post it on YouTube and I'll send a link around to the shareholders. I won't make it public, but just to the shareholders so that they can watch it in their own time. So you probably have a broader audience than we have here today.
Yeah, no problem at all. Yeah, like I say, this is a presentation I do regularly. I do it out to industry as well. So most recently, I did it in the Calgary Petroleum Club. So I'm based out of Calgary, you see. And later on in a couple of weeks, I'll be doing it at the International Pipeline Conference. So a lot of the conventional industry is getting very excited about nuclear and SMR. So
Yeah, yeah, it's a fascinating technology. I don't know. I guess it's hasn't quite caught on yet. Maybe I don't know.
started
I
to.
was watching that. I was watching that consortium of utilities in Idaho that was trying to build that SMR in Utah, and I thought that was pretty interesting. It was an interesting business model, first of all, because it spreads the risk. And I'm interested to see how these reactors shape up. So I'm fascinated to watch today. Um,
Fantastic. So I'm ready to go wherever you are, Steve. So you give me the heads up and the thumbs up, and maybe whenever
all
you want to
right,
shoot it.
all right. Give it one more minute. That'll be 1:05, and we can get started.
Yeah, no problem. No problem. Yeah, it's fascinating, and you know what's happening with Natrium as well, right? In Wyoming, Bill Gates' TerraPower with Hitachi, and up here in Canada, it's crazy. It's crazy how quick it's going. So, Um,
Ah, okay. All right. Well, why don't we get started, Jag? And thank you so much, Jag Singh, for being here to educate us. And thank you, Jason Hedin from Stantec, for helping organize this. And really excited. So please proceed.
yeah, brilliant. So let's do a quick test. So I'm Jag Singh. I'm with Stantec. I'm the regional sector lead for clean energy. For all intents and purposes, I'm the one that's looking after our nuclear division here, right? So anything nuclear comes my way, and I'm responsible for uh, for leading the team here. So, whoops, I don't know why that's not going across to the next page. Let me try it. There we go. So, just a quick safety moment. A lot of us we always think about safety as paramount, and it is absolutely safety is paramount. It's the heart of our nuclear industry, and there's a reason why we're the safest industry in the whole world, right? The significant checks and balances that are required as part of nuclear design go very, very deep into right at the core of everything we do. So even that is like you're walking up the stairs. It's how hold the handrail. Become indoctrinated in this philosophy where everyday life takes a different shape and different view. We also talk about security as well. It's really important to understand that you know. Security is quite important when we talk about information and technology. We've got to be really careful. I'll touch upon it a little bit later in the slides when we're safeguarding information. A lot of technology here, may end up having dual use, which is subject then to export controls. So it's really, really important as well. So safety and security in our industry go hand in hand. But just a little bit more on safety right here. You can see capacity factor by energy source here, right? Nuclear has the highest capacity factor. And what that means is it's the proportion of energy generating over a significant predetermined period of time, right? So all of that as well, in that kind of capacity factor is we get this much energy, but actually when you look at the amount of deaths that happen, this is fatalities with nuclear, including Chernobyl and Fukushima, we're at a mortality rate at 0.04 as an industry, deaths per billion kilowatt per hour. So we are the safest energy sector by far, even with those major catastrophes accounted for. Okay, so we're going to talk about how that comes to fruition a little bit later. Okay, so quickly, we're going to do a quick overview of the Canadian nuclear industry because this is a very Canadian-focused PowerPoint. But I'm also going to touch upon the US as well because I also have a foothold in the US as well with some of our team members. We'll talk about conventional reactor technology versus Gen 3 and Gen 4 SMRs and the difference between. We'll talk about some of the concerns in safety, waste, cost. Some stakeholder organizations, and again, I'll skew it towards the US industry. Design considerations, and we're talking about sector figures and just general infographics, which is really I find them really useful in kind of relaying messages out. So it's a lot better than just blocks of text on the slide. So this is currently the Canadian nuclear market. And what we have here is specific to SMRs is we've got utilities with SMRs within their sites and deploying those within their respective provinces. Okay, so that's MB Power for New Brunswick, and they're looking to put an ARC 100 reactor, which is a Gen 4 SMR at their Point La Pro site. Everybody is hopefully aware of OPG and what they're doing with Darlington, and they've got BWX 300s there. And most recently, and I work very closely with SAS Power, it's now the nuclear group is called SAS Nuclear, and that's recently been identified as the Estevan site, and they have two BWX 300s that are going to be going down there. So if we just switch it up to the US and take a quick look at what's happening over there, we got TVA, Tennessee Valley Authority, Tennessee Valley Authority, and they are also looking at putting a BWX 300 at the Clinch River site. We also have the Nature reactor, shovels in the ground in Wyoming. So they're moving in anger there. Dow Chemicals, I believe it's in Texas. We're looking at the industrialization part of this rather than the grid energy supply. And what they're looking at is a reliable baseload energy for their polyethylene plant, I believe, as a heavy industry. They're going to be going with X Energy for that. That was their current plans. Most recently, we started to see a lot of states start to drop the moratoriums that they had, there's a lot of moratoriums across. I think Illinois is one of the latest ones to drop it. I think the Palisades plant as well was another one where they're looking at dropping moratoriums and looking at starting to deploy nuclear energy once again. So this huge wave is going across the whole of North America and across the world, right? When it comes to nuclear and SMRs. So key within that is the US Department of Energy and the US Department of Defense as two federal entities which are really pushing ahead with this as well, really calling for this as well to start. And they do that notoriously by pumping a lot of money into the market and into the sector. So they have not just SMRs, they have intentions for conventional reactors, right? I mean, the US fleet is massive when it comes to conventional nuclear generating. Most of it's all Westinghouse, right? Westinghouse, the AP series reactors. And we're actually, I'm seconding to DWR as well, Department of Water Resources in California, where they're looking at refurbishing Diablo Canyon to get it the extended life. So you squeeze as much operational life out of the plant as you can. So the US is really strongly moving on, doing whatever they need to do to get nuclear energy front and foremost as that reliable baseload. So you sort of heard me touch conventional versus SMRs. What are the differences between the two technology types? So we'll just dive real quickly, and I won't bore you with this too much, but these are principles of nuclear fission, and key within this is just looking at the core physics of how nuclear energy is generated today. Okay, so this is fission technology. It's different from fusion technology, right? Fission is essentially you get a fissile material that is in the UK. We used a combination between plutonium oxide and uranium dioxide, and we mixed it to form mixed oxide as a fuel. Here in Canada, CANDU fleets operate on low enriched uranium, which is uranium with a slight proportion of it at a higher fertile isotopic range. But once you get this fertile material and you put it into the right configuration and you apply the right conditions, be it through a moderator or wherever that ends up looking like, you can get the right spectrum to get fission to occur, which is essentially getting the right energy range for neutrons. As they get emitted, they collide with the other fertile material. And in that collision, we see the atom split in here. Okay, so here's the impact, and it splits into two, which produces 3 more neutrons. And now you have this chain reaction, and they produce 3 more, and they produce 3 more. So you end up getting this this chain reaction that essentially, as you're splitting the atoms, we produce energy, a whole load of energy, but also radiation in the form of gamma rays and beta particles. Okay, so when we talk about nuclear waste, I just want to bring your attention to something really key here. We're actually talking about these daughter products, okay? These daughter products are often what's regarded as nuclear waste. Okay, so what does a nuclear fuel look like? We talk about atoms, but let's visualize it a little bit. Typically we have metallic fuel in conventional reactors. If a car uses gasoline and a truck uses diesel and a plane uses kerosene and a rocket ship may use hydrogen, this is what the fuel looks like for a nuclear reactor. It's no bigger than the size of your thumbnail right here. It's tiny. Okay. So all the reactors in Canada have uranium as a base fuel, and they'll be right now in the conventional reactors, they're solid metallic fuel pellets. But some of these advanced small modular reactors, the Gen 4 small modular reactors, are starting to use liquid fuels. So the company I worked for before I joined Stantec is a company called Maltex. Okay, I was head of their engineering team there, and we were developing an advanced SMR, Gen 4 SMR, and we actually used liquid molten transuranic salts as the fuel. So it's really unconventional to use a liquid nuclear fuel. But that's the technology that's being developed right now. And I believe even in the US, you had the EBR2 prototype reactor. So this technology, although it's coming out as being this whole new, a new foray on the frontier of science and technological innovation, SMRs have actually been around for a very long time, either in prototype phase or you'll find them in the back of a nuclear submarine or maritime purposes, right? So SMRs exist, and here's typically what the fuel looks like. So we talked about CANDU there, and it's there's a spectrum of there which is only 0.7%, which contains that fissile uranium, and the rest is actually just natural uranium. Okay. Light water reactors, again, this is what you have in the US. They'll have uranium that's enriched, so you have a larger proportion of it, which is that isotopic element. And many of the new advanced small modular reactors actually have enrichment levels to 7 to 20%. And that's where we hear the term HALEU. So a lot of the SMRs use HALEU. We'll go into some of the problems with HALEU in terms of just supply chain, right? Well, a lot of it we were procuring from Russia, and obviously we can't do that anymore. So we're seeing this big push in the US to now start domesticating that supply of HALEU. We're going to need it for the advanced small modular reactors. Okay, so let's have a quick look at some reactor technology types. Okay, this is a pressurized heavy water reactor. These are all CANDU reactors here in Canada, our conventional reactors that are in existence. And this is what that CANDU fuel bundle looks like. So within each one of these pins here, we have those pellets, which I just showed you, no bigger than the size of your thumbnail here. And we have those stacked up within each one of these. So memory serves me correctly, we have around about 17 of these fuel pellets in each one of these pins. We have 37 fuel pins that make up one fuel bundle. And then one of these complete fuel bundles is represented by one of these red and orange blocks right here. That's the nuclear fuel. And what we do, we circulate that heavy water, which is deuterium dioxide, D2O, to get the right conditions in the physics, which is slowing down those neutrons to the right spectrum so that we can get that fission taking place. And the benefit of CANDU is we don't have crazy pressurized, pressure vessels and things like that. Okay. We do have high pressure systems, but we don't have pressure vessels. And we end up not needing to use plutonium because we are a non-proliferation state here in Canada. So we don't use plutonium here. So we can use natural uranium. And that's the biggest benefit of this technology type. We don't have to have, very, very large centrifuges to get enriched fuel. Okay. So let's compare that to an SMR. A small modular reactor, look at the size difference already. You got a small person right here next to an SMR, and that's a core. And look at the size of what you need in a conventional reactor. We produce 300 megawatts electric, typically around that range, 100 megawatts electric. And we get economies of scale. So We end up with a compact design, and the idea, the whole idea between, behind SMRs is actually machine line fabrication. You're supposed to be able to run these off a machine line, and off-site modular construction, modular build, off-site work acceptance testing, and factory acceptance testing, because a lot of the cost of construction delays can come down to having to do all that activity on a nuclear licensed site, which can make it very prohibitive from a cost perspective and a timeline perspective, because you have to have all the extra checks and balances. One of the biggest parts of SMRs is walk away safe. All right. So in some of the reactor technology types, and I'll go into a little bit later, some of the reactor technology types, they actually are, they shut themselves down. It's impossible to have a meltdown because they have a negative void coefficient, which means the hotter it gets, the less reactive it gets, and it just shuts itself down. Okay, and we also have reduced waste. We'll go into that in a little second. I'm going to skip over this slide real quick, but there's two kind of reactor technology types, getting heavily into the physics here. So this is fast spectrum versus thermal spectrum, but I'll go into that in just a second with the reactor technology types. So here's the GE Hitachi reactor, the BWS 300. Okay, so this is more like a conventional reactor. It's a boiling water reactor. It's based on that technology, which is why it's got so much traction. But it's still a Gen 3 reactor. Okay, so notice the refueling cycle. This is how often you need to replace the fuel. And also notice that you're having to pump water into the core and get steam. It's boiled and you get steam out that drives that turbine. And that's your primary circuit, right? We'll jump over to a Gen 4 reactor. Now, this is the arc reactor. So this requires sodium metal coolant, so liquid metal coolant. Now, the fuel type changes here, right? Because now what you end up with are these HALEU pellets. And because of the reactor physics technology, the modeling behind this, you only have to refuel one of these every 20 years versus every 2 with a conventional reactor. So you can drop one of these down in a remote location, a remote site, and you won't have to touch that fuel for 20 years. That's currently what they're looking at. Now, another key difference here is the outlet temperatures of these. So this is why a lot of the oil and gas industry up here and some of the mining industries are starting to look at this as a reactor technology types, because you actually produce very high temperature steam, which is directly applicable into applications such as oil sands and other heavy industrial processing. So again, it sounds quite exotic with liquid sodium as the coolant, but actually, prototype reactors, this goes right back to the Dounreay Fast prototype reactor back in the UK. And that was back in I think the 70s or the 80s, they had that reactor technology type as a prototype. Here's the company I work for, Moltex, and here we have liquid fuel in channels. And then we have a liquid molten salt primary circuit here, and a secondary circuit is that steam cycle. So again, we're starting to look at molten salt as an application, and the beauty about this reactor technology type is you can take existing spent nuclear fuel that's currently seen as a liability across the entire world in some respects, although this technology is designed for the can-do spent fuel for now. And you can actually recycle that fuel and use it as new reactor fuel here in this sister SSRW. And what that means is at the moment, the can-do fleet stores their nuclear fuel in that metallic form that I was showing you earlier, those can-do fuel pellets. And actually only 80% of that, 20% of that is used in the fission process. 80% of that fuel pellet is actually still unused. So if you can separate out 20% from the 80 and take that 80 and turn it into new fuel, then you're essentially, hugely increasing the efficiencies of that waste. So that liability becomes an asset, and you can burn it. It's what's called the SSRW, the waste burner. You can use it in this reactor. Here's another one. It's a terrestrial reactor. And again, this one gets really exotic, right? In this one, you're actually got the nuclear fuel recirculating around a static core. So these are graphite moderators. Okay. So you recirculate the fuel, which is really unheard of. And the temperatures that you get up to are here. And again, each reactor technology has its pros and cons. But this is one in development as well. So yeah, it's a really fun time for reactor technologies. And there's a lot of SMRs in development stage. There's a lot that actually, there's quite a few that are actually in operation. It seems to be, perception out there that there isn't any proven technology out there, but there is. There is out there. So, we've got the PWRs, the heavy water reactors here in India, PWR in Russia, and integral PWR here. And there's a few under construction. So it's quite important to understand that. Okay, so we get to a few issues and challenges and concerns, right? Typical ones we hear are, what's the waste? What do we do with it? Aren't these expensive? And they're not safe. Given historic issues with Chernobyl and Fukushima and 3 Mile Island, it's really important to start addressing these to a wider audience. So let's have a quick look at the negative void coefficient. Here's a safety example. I talked about it a little bit earlier. SMRs use passive safety systems that rely on natural phenomena, right? So we don't have active shutdown systems really anymore. The Maltex reactor actually had an actual emergency heat removal system which had no active components at all. It was all passive. And a negative void coefficient is a great example of this as well, right? So this is essentially as the reactor gets hotter and hotter and hotter, you end up with these steam bubbles forming in the coolant, which gives a negative feedback to the actual reactor. And if it starts to overheat, the more those steam bubbles get generated, then that reactivity decreases, which, this is a self-regulating feature. Okay, here's another one. Versus the reactor technology itself, the actual fuel is now becoming safer and safer and safer. It's a trisol particle. Depends on which accent you're using, but yeah, trisol particle. And this is being developed in the US with USNC and X Energy are also going to be using this specific fuel source in their reactors. All right, so where I talked about those pellets a little bit earlier that are held in sheets and rods, these are actually little balls, and the fuel itself is encapsulated. Okay, so these pellets have been tested to withstand really extreme temperatures and really, really, harsh environments. And they keep those fission products, which I showed you right earlier, those daughter products. Those fission products, which is the waste, they're all retained within this particle. So you can imagine how appetizing this becomes for either when you're refueling or waste management or anything in between. So safety is now being innovatively ingrained, not only in reactor technology type, but the fuel itself. So we're just seeing things get safer and safer and safer. Okay, so when we talk about waste, it's really important to address this. Most of the waste that we see that coming out is actually LLW, and we talked about that unused uranium, the 80% there. Only very small amounts of this is actually considered high level waste. Okay. And the reason behind that is because actually those daughter products, the most radioactive material that's produced as part of the nuclear process, a nuclear fission process, is 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 that half-life. It decays really, really quickly. So some elements and components are actually around for even a fraction of a second. So really, the more dangerous things are in terms of nuclear waste and high-level radioactive waste, the quicker it decays away. So this is why we end up having storage ponds on nuclear reactor sites. So as soon as that fuel comes out, it goes into a pond and it'll stay there for 7 years. And this is where they let it cool, which is letting the most radioactive components within that fuel to decay away. Okay, so you end up really with most of that waste now being ILW and LLW. Okay, so it's really important to understand that. And then when we start looking at the amounts of waste, this one's really, really key. And again, I'm going to start going into infographics, get into infographics heavy here. So if the US has produced roughly 83,000 metric tons of used fuel, which is the entire fleet generating over 60 years, I believe, all of that could fit on a football field at a depth of less than 10 yards. That's the entire amount of nuclear waste that's produced. So let that thing at 60 years of the entire fleet of the US, that much energy that's produced. Okay. There it is right there. And it's really dense, okay? And that's the reason why it's all kept within this. And remember, this is all carbon free. So you're not having any carbon dioxide emissions really as part of the process here that's producing that. It's carbon free. So it's truly clean energy and it provides that stable base load as well. So when we talk about solar and wind and all the intermittent supplies, yeah, I mean, they're also carbon free, but you know, when the wind isn't blowing and the sun ain't shining, that energy capacity comes into the factor, and you're like, well, actually, you know, your actual waste produced per unit of electricity that's generated is actually quite high. So when we start looking at some of these, you know, if you say per person, in the UK, we have quite a big nuclear program, and they produce 0.84 liters of waste per person. Of that, most of it's low-level waste. There's a lot of it which is, you know, or I should say a small portion of it which is intermediate level waste, and a very small proportion of it that's high-level waste. So this is the one that's really dangerous, but per person, every year, it all fits in a bottle that big. And that's for everything. We're talking about in that person, that's the food that they eat, that's, you know, that's the energy that's required for, you know, the houses, for the clothes that they wear, for everything. Okay. So we talked about reprocessing and recycling. And then, you know, in the UK and the US and France and soon to be Canada, they have those recycling, reprocessing technology where you can take new nuclear waste and recycle it and reprocess it. All right, so let's have a quick look at the economics. Now, with the economics of a nuclear reactor, you hear overnight capital costs, and that, you know, I guess a lot of people are a little bit scared, right? You know, they hear $1 billion of plant. But it starts making sense to look at nuclear when you look at the levelized cost of electricity over an amortization period of about 65 years, which is the life of a nuclear plant. And you can do plant lifetime extensions onto that to get even more out of it. But when you start looking at the LCOE over an amortization period of 65 years, we start looking at things that become very competitive, really competitive. Okay. So I'm going to quickly jump down to the bottom here and just give you a quick figure here, right? So when we look at all these SMRs that are coming out right now, those LCOE figures, they range from $36 per megawatt hour to $90 per megawatt hour, with an average of $60 per megawatt hour. Okay. The first of a kind, absolutely, you know, that figure might be quite a bit higher than that. But the nth of a kinds, where you start capitalizing on economies of scale and things like that, really starts bringing it down into a range, which makes it very competitive with some of the other plants out there, right? And other technology types. Okay, so energy density. And the reason why it is because of energy density. All right, so let's have a quick look at this. The heat value of a fuel is the amount of heat released during its combustion. That's the calorific value. So if we take one of those pellets that I just talked about, and we compare it to natural gas, for that one pellet, you need 17,000 foot cubed of natural gas. You'll need 120 gallons of oil, and you'll need a ton of coal. Less than 10 of those pellets can power the average household for a year. Okay. Going back to what I was talking about, recycling, reprocessing, while the US generates about 2,000 metric tons of used nuclear fuel a year, spent fuel still contains more than 90% of its potential energy. I use 80% in Canada, but 80 to 90% is unused. You can recycle that into new fuel. And we're talking about conventional fuel there. So let's apply that when we start looking at some of the other reactor technology types. Natural uranium and a fast spectrum reactor, you're now at 28,000 gigajoules per kilo compared to all these other ranges here. And when you start enriching uranium up, in a light water reactor, you're talking about 4,000 gigajoules per kilogram. Massive amounts of energy. And here's some more infographics. And, how long will a pound of fuel power a light bulb? Coal, 2 days. Natural gas, 3 days. Uranium in a light water reactor, a conventional nuclear reactor, 64 years. In these advanced SMRs and reactors, 2,000 years almost. You could power a light bulb. Okay, and here's a comparison to wind and solar. You can see you need 3.125 million PV panels to get to the same amount of how much a nuclear reactor will produce, and 431 utility scale wind turbines for the same reactor. I won't go over into these ones. You got a copy of the presentation there, and it just goes on and on. It just shows you how efficient it is. Okay, I'm getting close to time on this, so I'm going to quickly skip through some of these, but radioactivity is a key one I really like explaining in some detail, because this is a key one to get a real perspective of radiation and a lot of concern out there in industry. And we use bananas to do so here in this specific presentation, right? Let's contextualize it. If one banana, you have 0.1 microsieverts. You actually pick up radiation by eating a banana. So if you had a banana today for breakfast or any part during your day, you picked up some radiation right there. Now, if you live within 50 miles of a nuclear power plant for a year, it's less than the dose you just received today from eating a banana. What about if you go through an airport security scan? You get 2.5 bananas right there. A dental x-ray gets significantly more. Okay? You spend a day on Earth. You got a couple of crates there now. How about a flight from New York to LA? And I think about this. I was just in Arizona last week, and I was thinking about this specific infographic when I was there on that flight. We end up with 4 crates of these bananas. Living in a concrete, stone, or brick building for a year, you get more. Now, average dose within 10 miles of a 3-mile island accident. This is how many bananas you end up having. Actually, within 10 miles of that 3-mile accident, that's how much dose you received. Spend an hour 2 miles from Fukushima, 2 months after the accidents. We got barrels full of this now, right? Or I should say a barrel and quite a lot. However, 6 months of eating food, you receive more dose from eating food than you did from spare an hour, 2 miles of Fukushima, 2 months after the accident. Mammogram, CT scan, smoking a pack of cigarettes a day for a year. You're in the truckloads now. Dose of which an increased risk of death from cancer is evident. Look how many truckloads you get in there. Okay, so it goes on to Chernobyl, and obviously that was a very serious incident, and a lot of people got a significant dose. And temporary radiation sickness, but not fatal, you end up with shiploads of bananas that are required for you to get sick, but not fatal. However, the fatality comes in. This is how many bananas you're going to have for a fatal dose and death within 2 weeks. So it's really important to understand the context when we talk about radiation. It's actually very, very safe. Okay, I'm going to skip over these ones. This is CNSC. If you'd replace this with the US NRC, the Nuclear Regulatory Commission, that is the regulator for the United States. IAEA is the overall umbrella across the world, and the US NRC has to link up with the IAEA. They're essentially, for all intents and purposes, kind of the parent organization to make sure, the IAEA is mostly about peaceful use of nuclear energy and making sure we implement the right safeguards. The US NRC will start putting regulatory oversight onto specific how you execute design. For example, here's the Canadian version. The NRC will have their own version. The licensing with the US NRC is different to Canada. This is Canadian. With the NRC, what we're starting to see with SMRs is a combined license application. You typically have a couple of licenses that you got to have for a nuclear power plant project, an SMR project in the US. For waste, we have the NWMO here in Canada, and I know you've got Yucca Mountain, I believe, for your deep geological repository. Although I hear that's put on hold. But the US, in fact, I don't know too much about the US waste program, but I believe it's all privatized for the decommission aspects of that. So don't quote me on that. Yeah, I'm not too sure on how nuclear waste is handled in the US, but I believe it's still tied to those facilities that hold the license. A huge emphasis for us is First Nations communities and making sure First Nations communities are involved in the planning and implementation of those facilities and waste facilities. Okay, so ALARA, Defense in Depth and Design, we have to go to level of substantiation that is typically, outside of conventional nuclear plants, conventional energy plants. Okay, and the idea here is we want terms as low as reasonably practicable or achievable, and we want to mitigate any kind of issues that may arise. So, I've got a background in offshore oil and gas as well, and there we have our checks and balances and HAZOPs and whatnot. But here, safety is really, really ingrained from first principles engineering. And that risk profile is mitigated through design. So we have various levels of defense in depth here, right? So prevent deviations from normal operation, detect and intercept deviations, minimize the consequences of level 3 of accidents. Level 4 is to ensure radioactive releases are kept as low as practical. We should never get to that stage anyway. And level 5 is mitigate the radiological consequences of potential release of radioactive materials. Everything about safety in the nuclear aspects of the biggest parts of that nuclear sector and nuclear engineering is around about confinement of radiological material. It's really, really important. That's what safety cases, nuclear safety cases are about. the emphasis is on confinement of radiological material. So that's why the containment structures, they have to be designed to withstand aircraft impacts from Boeing 747s, for example. So you wouldn't need that on an oil platform, but you need it on a nuclear platform. Anything that can relate to a release of radioactive material has to have a safety mech, a safety function, which is a 10 to the minus 5, 10 to the minus 6 incredible event. Okay, so that's the level of design we have to go to. And this is why our plants are so safe. Okay, so this is an overall market economics piece. And I'm going to finish off with just, talking about global market for SMR is technology specifically is estimated to, 400 to $600 billion. Okay. This is why you're seeing so many organizations and such a fire started for the nuclear industry, the SMR industry, and there's such a push now because of the significant amount of potential market revenue that's achievable within organizations. So if the capital cost of a new build is estimated between 300 million and a billion for a first of a kind SMR, this is a multi-billion-dollar market just for SMRs in Canada alone and the whole of North America. We're talking multi-billion-dollar industry. Okay. The IAEA, which is that global umbrella I talked about, they've got some projections, and they're talking about 390 gigawatts to almost 500 gigawatts of electricity by 2030. And we saw during the COP and the Climate Action Summit, there's a declaration to triple nuclear energy in 20 countries and 4 continents. They signed on to that, which is hundreds of billion-dollar, potentially, even perhaps even $1 trillion industry globally, if we start looking at what that really entails. So we're talking about new build here and market potential. But when you look at plant lifetime extension, maintenance, operations, decommissioning programs, this just goes on to hundreds of millions of dollars and billions of dollars over, the next 100 years or beyond. Some of these decommissioning programs in the UK that I've been a part of, they're billions of dollars every year into the supply chain. So key messages going out to industry is, be an early adopter, get in there early. Do not be the last at the table there, right? Or a last off the fence there, and taking account and capitalizing on this early engagement. And you benefit from clean energy, reliable baseload power, strong, stable, long-term projects with a whole lot of revenue there. So that is the end of my presentation. I'll open it up to questions and closing out.
Tom, do you have any questions coming in? Or we can just open it up. There are many people on the call, so anybody that has a question.
Yeah, we might just open it up, Steve. I don't have any questions listed in the chat.
Sure.
But I had a question, if I could ask Jag. You mentioned refurbishment of Diablo Canyon, which I was interested in the potential for refurbishing existing nuclear sites. And when you talk about a 300 megawatt kind of maximum for the SMRs, does that mean you have several SMRs with one steam cycle for, let's say, a 1200 megawatt steam turbine? What are you thinking about that, and how much of the existing infrastructure do you use?
So yeah, 2 great questions. So I'll start with the refurb first. So Diablo Canyon, plant lifetime extension is nothing new. I was doing that in the UK fleet, in the early part of my career. So that refurb process is essentially going through, you do the interviews with the system engineers, and you go around and looking at the condition of components, and you do some corrective maintenance and preventative maintenance, so you can squeeze out that plant lifetime extension. Everything comes back to that safety case, right, at the end of the day. So so that's happening at Diablo Canyon. You're going to see that happening more and more, because it's actually quite a it's quite an cost-effective way of squeezing out more power. If you've got most of that capex built, that's spent, then why not just upgrade specific components, plant, and whatnot to squeeze out more energy out of it, right? So now, just on that though, it's not limited to nuclear, right? So conventional plants are now also being teed up. Where we have power stations here in Canada, a lot of the studies are now looking at repurposing that infrastructure that's already there. A lot of it's the same in the balance of plant and replacing that heat island from a coal plant to a nuclear plant or SMRs in this case, right? So those studies are going on, and that plant lifetime extension is not just limited to nuclear plant. That's a key message I want to get out there. So there's studies on so for example, the Estevan site that I talked about, where SAS Nuclear have selected that. That's actually a conventional site there already. So they're already looking at doing that. So that's the key bit on refurbishment there, and you can extend a plant lifetime. I mean, Diablo Canyon, they're going for another 5 years there at Diablo Canyon, which doesn't sound like a lot, but that's 5 years of clean energy and reliable base load. And we know California needs it, right? So that's an important aspect to understand. So your second question on the 300 megawatts electric. So it depends which reactor technology type you select at the end of the day. I mean, the terrestrial one, I think, is a 400 megawatt electric, but typically 300 megawatts is what's kind of deemed as a limit, for SMRs. And you're absolutely right. The whole point of SMRs is a small modular reactor. So, SAS Power themselves, SAS Nuclear now, I should say, as of a couple of weeks ago, they're going to initially start off with 2. But the second phase will probably get up to about 8 of these SMRs, and typically what you'd look at is depending on how you do your engineering balance of plant and depending on what that loading's looking like, you could squeeze in 2 if that Estevan site for the rest of the balance of plant is capable of handling the rest. You'd have to do some modifications and tweaks to existing infrastructure, but typically. If you're doing it from a greenfield site, you'd end up having your own loops. Is the way I'd go around designing that, right? So you'd end up having your own steam cycles, your primary and your secondary coolant circuits. You'd have them independent of each other and run them as trains, essentially. The downstream side of that to the switchyard and grid connection, obviously, is where you consolidate a lot of that. But trains is the way I'd go if you're doing a greenfields site. Does that answer your question, Son?
Yeah. Another question I have would be, what is the turn down ratio of an SMR? Is it similar to large nuclear plants? Are you kind of limited to how far you can turn it down?
Typically, you mean turn down in terms of power? Or
and can you run it 30%, or do you have to run it 95%, or how easy is it to dispatch down from full output?
So I think it's not ideal, right? I mean, you wouldn't want to be peaking a trough in a nuclear reactor, really. You want to get it to a band and run it at that band. And the reason I say that is because a lot of these SMRs, they're coming out with so for example, giving an example is the SSRW, the Maltex, where I was with them. They actually have these molten salt tanks called grid reserve, right? And what that does is, any excess energy that you're producing in thermal capacity, you can load them into those storage tanks and actually store that energy as in the molten salt there as a heat. So if you're getting these kind of peaking demands on grid or whatnot, you can use it, you can utilize that to smooth out those curves. But typically you wouldn't really want to be dropping it out of those specific bands, because a lot of these reactor technologies now, they're not looking at control rods in the typical sense of what you would have in a conventional nuclear reactor, right? A lot of them are just loaded up, and especially the fast spectrum reactors, and they're just run flat out, right? So that they don't lend themselves well to those kind of extra controls. Starts to go away from the benefits of just keeping things real simple, keeping things real cost effective. Um, and so yeah, excess energy that you produce, there's other ways around storing that.
Yeah, I have a have a comment and question related to that. Traditional nuclear reactors or conventional nuclear reactors have had two really significant problems. One is cost overruns. Normally, with a large, complex piece of machinery, the more of them you build, the cheaper they get. Nuclear is just the opposite of that. The more of them you build, the more expensive they get, historically speaking, which has been a huge problem. And related to that is the topic that Tom just brought up, and that is that in order to keep your power costs as low as possible, you have to run them at full speed. Even if you could run them at lower speed, you can't afford to, because that makes your cost of energy go up, because most of your cost of energy is capital cost. Now, the question is whether small modular reactors are going to have those same two problems. There have been two small modular reactor programs in the United States that have been canceled, one in Idaho and one in Utah, because of cost overruns, which does not bode well for the future. But the other issue is, just in terms of the power system in general, in order to get minimum costs from nuclear reactors, you have to run them at full power. The grid doesn't like that. The grid doesn't run at full power. The grid varies all over the place. So, as you just mentioned, certain kinds of reactors can store excess energy in terms of heated material, which could be very valuable. The natrium reactor that Gates is funding does that. That's a huge advantage compared to conventional reactors. Most of the other small modular reactors, however, don't have that capability. So isn't it true that they're going to need a lot of energy storage to make them viable in the marketplace?
So yeah, so two great questions, right? And this is the ones I always stumble across, right? Is the cost overrun piece. So if I address that first, so yes, you're right, right? Conventional reactors cost overruns. Now, SMRs, again, the whole point of this is the nth of a kind. If you take that same reactor technology, and you run that out, could you say that's the same for, let's say, the maritime applications, right? So if you're going to nuclear submarine or a nuclear ship and you have an SMR that's modularly built and modularly, offsite tested, commissioned, etc., using that same philosophy and put it into a maritime, is that the same? Have they been exponentially increasing over time? Now, I don't think the answer is yes to that. And I think the whole point, the whole reason behind it is because of the SMR's kind of, the application of it in terms of that modularization build. Now, I can speak to this because Hinkley Point C in the UK is drastically overspent. So if you scratch beneath the surface, you have to start wondering why. What are the reasons? Like, what is leading to these cost overruns? Regulatory oversight is a big one, right? Here in Canada, they're moving heaven and earth to try and get that regulatory oversight significantly reduced. Okay. The project personnel, how about that, right? Just the amount of project personnel that you need on a conventional reactor. How much of that is bespoke and only nuclear engineering? Now, that changes a little with the SMRs, because what you're getting is a standard design. That's the whole point. So Hitachi have a standard design, which is, here's a nuclear island, standard design. Here's how it's going to be built. And, OPG will be the first ones to take the big hit on costs, right? Once you get that standard design, then everybody else, all the other utilities across the world, then only need to decide specific engineering, right? So that becomes a whole new slant on doing conventional reactor engineering, conventional nuclear engineering versus those specifics, which then is down to a steam cycle at the end of the day.
Except that in your presentation, you showed us about, I don't know, what, 15 or 20 different standard designs.
Yeah, that's that, and that's a great point, right? So this is why everyone's going for the G-Hitachi. So if you look right now, most utilities, Darlington, Saskatchewan, Alberta, where I'm based, right? TVA, and others, they're looking to that. That's one standard design for all those utilities and all those
Mhm.
deployments. That is one standard design.
Yeah.
In reality, all those are the reactor technologies that I showed you there. In reality, there's not going to be 15 standard designs. They're going to be a front runner for a Gen 3, which is BWX 300, and there'll be one or two front runners for the Gen 4 reactors, which is probably going to either be X Energy or the Natrium reactor. And mind you, GE Hitachi is part owner in the TerraPower, the Natrium reactor there as well, right? So even between them, there's interlinks. So what that comes down to is then, as a nation, which as a sector, which reactor technologies is your country going to get behind, right? Is the industry going to get behind? So that's kind of the ethos and the nth of a kind. They start taking a fleet approach, right? So Hitachi and OPG now start taking a fleet approach, for example. So there's all these kind of innovative ideas that are floating around on how you actually deploy these cost effectively, right? So that's supposed to be the difference between SMRs and traditional nuclear reactors. Whereas a traditional nuclear reactor, each project is its own behemoth. SMRs is not supposed to be that way. Okay.
Yeah.
All right. And the second question you had was on
Storage.
storage. Okay. So excess energy is never going to be a problem here in Alberta, right? We're on rolling blackouts, so that's not an issue here, right? Now, a lot of these are starting to get seriously considered by data centers and AI centers and heavy load technologies like that. There are battery technologies out there as well. So if you're producing excess power, you can either, again, use that thermal storage process as a technology, but there's batteries now available as well, right? In industry, where you can load them into battery technology as well. But really, because it's 300 megawatts electric or 100 megawatts for the arc reactor or anything in between, we start looking at like, is it really going to be a problem running that out at max capacity all the time? Is that really going to be an issue, or is that an opportunity? So I'm helping SAS Power and SAS Nuclear. I'm helping them with their overall utility strategy right now. And we started asking some of those questions. And the conclusion we get to is you can never really have too much power, right? They interconnect out to another municipality, or in this case, a province, and you can sell that energy out. And the PPAs, and that's the reason UAMPS fell over at the end of the day, the Utah SMR.
Except in major markets, the way that excess energy is handled is they curtail the production.
Yeah, they curtail the production. But in the nuclear world, and they do it in NB Power, and they do it in the UK and beyond as well, you sell out. You basically have a PPA and you sell that excess energy out, and they sell out to Maine, I believe. So if you position it correctly, so with SAS Power and SAS Nuclear, with Estevan, they have the option, and this hasn't been decided at all, but they have the option of, selling out to North Dakota or Alberta or elsewhere, as long as you get the right PPAs in. You have excess energy, someone's going to always need to use it, right? So,
the curtailing is saying that's not true.
Oh, really? Where is it based out of?
I would say, though, Jim, that this is an opportunity for gravity power. I mean, one of the reasons we're so interested in this technology is the natural marriage between SMRs and GPPs.
That's the point. That's the point.
Yeah, exactly.
They're going to need storage just the way conventional nuclear power plants needed storage 60 years ago.
Yeah. So how about this? So if you have your stable baseload power from your nuclear reactor, then does it not make sense limiting your other technologies? So, you ramp up this one and you bring the other ones down.
In the marketplace, the answer is no. because in major parts of the marketplace, you have other sources of power that cost a half or a third as much as nuclear power. So if you're buying power, who are you going to buy power from? The most expensive provider or the cheapest provider?
Yeah. So you can either store it, or you can get PPAs in neighboring states or wherever it is, and you can sell excess power. And if you're saying that you can't do either of those, then you probably have too much power to begin with. If I'm being totally honest with you, it's. Sorry, where are you based out of?
California.
Yeah, I thought you're having serious issues with power there, because we are.
Well, one of the big issues right now is that solar energy is maxed out.
Yeah.
The incremental value of solar energy in midday is now zero, because it saturates the market. So we need a lot more solar generation, but only with storage. If you don't have storage, it's valueless. If small modular reactors took off and became very popular, exactly the same thing would happen to them.
Yeah. So you're saying you have too much power for the California grid
at certain times.
Yeah.
And because the grid varies all over the place in the demand, the same thing is going to happen to reactors if you're successful.
Yeah, I always thought California, especially my conversations with DWR and co, was that you can't get enough power. You need more with the data centers, more with the AI, more with the desalination plant, et cetera, et cetera, et cetera.
It depends on the time of day. We have the famous duck curve. If I may, Jim, interrupt this, we're a few minutes over. Jag, if you have time for one more question, Bryant has posted something in the chat. Bryant, do you want to go off mute and state your question?
Yeah, for sure. Thanks for all the powerful information. Thanks for the good, challenging question, Fisk. That's a really good question. I was wondering a similar thing. So, like you just highlighted, this was part of my question, is a lot of times when you see these advanced technologies come through the pipeline, they're the big fish in the pond, and everyone else is just swimming around to see how they're going to enter the pond. So how are you handling all these big fish entering the pond at the same time? You have small modular reactors, which I'm a huge fan of. You don't have to sell me on that even for 5 seconds. Small modular reactors. Let's see what else. Wind and solar, which, like Fisk said, are powerful sources but are intermittent. What else? I mean, there's the full gambit. So how are you handling this complex landscape? Even in nuclear, there's a lot of advanced players just coming out in nuclear, but in the greater energy landscape, how are y'all working together since there's so many big players entering the water at the same time?
Great question, right? So brace yourself for this then. It's basically there is not enough resources, there are not enough organizations to support the nuclear ambitions of Canada and the US, right? It just isn't. So, Canada, I can speak to a lot more strongly. We're saturated with utilities that are going out and making these grand plans and the whole SMR roadmap. And then, organizations that are out there, major engineering firms, if they secure all that work, we're talking billions of dollars worth of work here and huge programs. There is not enough organizations out there that can actually support that, right? So it's actually the other way around. We specifically here at Stantec, as an engineering organization, we're having the opposite, right? We're having organizations and utilities come out to us now to say, hey, we need a pool of resources. We need support because some of the other programs in Ontario are sucking up all the Ontario teams. Here in Western Canada, they're like, well, where are we going to get the resource and where are we going to get the engineering done? So it's actually the other way around. And to be fair, with some of the utilities out there, and a lot of utilities jumping onto this, they're the early adopters. And they're the ones that are going to direct really where the industry goes. We were talking about it earlier. We're not going to go with 10 technology types. We're not. We're going to go down with 2 or 3 technology types. So really that they're going to dictate which technology types get adopted. And I stay in touch with provincial governments, and I'm active with governments as well. But really it all comes down to 1, a monetary decision, but 2, technology readiness levels as well, right? I mean, you're going to start seeing investment firms and government entities shy away from technologies out of paper reactors or a TRL level 1 or 2. They're just not going to touch it. So that's why GE Hitachi was kind of pushed as the early adopters here as well, because they have a high TRL of technology that's based on the boiling water reactor of GE technology. So yeah, so I'm not sure if that's kind of answered your question there, Brian, but it's actually the other way around.
Yeah, it does. It does for sure. It sounds like y'all are taking and this is kind of the trend is y'all are taking a top-down approach where we really need an iterative bottom-up approach so we can realize these benefits in sync with the resource that's available. But I do a good amount with some big corporations with hydrogen, big and small corporations with hydrogen. And I'll say this, and I'll let it give it back, is that I think the problem is where every other implementation, it's been an implementation of what, not how. And so with the energy implementation, you're going to see you have a lot of various use cases, geographic, end user, stakeholders. You're going to see people wanting to pair geothermal with their small modular reactor, with their data center, with their natural water resources. So it becomes it almost becomes more about how can you strategically pair and broker those resources than the resource itself, because we know they're all going to work. We know wind's going to work. We know pumped hydro work. We know all these things work. They're proven technologies, but how can we strategically pair them together for a distinct point-to-point need? And I think that's what's kind of going over a lot of our heads, because it's just muscle memory, right? Like, what have we been doing for the past generations? Is finding one solution and just cranking it out. So I think that's the shift that we need to make. Is
so if I may,
go ahead.
Yeah, if I may. So with that specifically, sorry, a bit choppy there as well, Brian, and there's a bit of feedback on there. But yeah, I'm sorry to hear you. But yeah, Saskatchewan has just gone down that path where you're talking about, right? Their bread and butter was conventional energy. And again, a lot of it gets driven by one, incentivization by tax credits or whatever else for low emissions, no emissions. But pairing it up is exactly it, right? So we touched on it a little bit earlier with Jim there as well, which is you have intermittent supply and you have stable baseload energy, right? And if you look at the way the UK did it as well, they've done it. They've got stable baseload here. They've got a bit of renewables, and really comes down to this: every utility has got to go for a good energy mix, And I think Alberta's realizing that now, real carefully. We're an oil province. We're an oil capital here, right, in Calgary. In Alberta, and even Alberta now is switching gears into, we need to supplement oil and gas with nuclear, right? We need stable baseload, but be able to have that intermittent supply as well. And yeah, you got to pair it up, but it depends on your industries as well, right? So if you've got a heavy, let's say, oil and gas industry, that it's got to work in conjunction with that. But if you're starting to produce AI centers and data centers, which are really power intensive, and you need that stable baseload energy, you can't rely on that intermittent supply, right? So it's really got to go hand in hand with your technologies and your sectors within wherever your province or state is. And again, I keep going back to AIs and data centers because that's essentially, going to be the future here as well. And you're going to see a lot of countries and states and provinces adopting stable baseload energy, where again, intermittent supply may not just cut it. So there's going to be a whole lot of
I'm a big fan. I'm a huge fan of what SMR does for just balancing it. I think at the end of the day, it's a brokerage problem, and we haven't fixed a problem like this in the energy industry because it's been heavily regulated, and at least I'm speaking to America, it's been heavily regulated. But this is a brokerage problem. It's not about can you create the energy; it's can you get the energy and network it to where it needs to be, or store it for later usage and profit optimization at a later date. So it's a brokerage problem.
Yeah, absolutely. I think you're right.
Thank you so much. Like I said, huge fan. You keep working hard.
Right.
Thanks for that question, Brian. Jag and Jason, you've been very generous with your time and your knowledge. It's just been terrific. I've thoroughly enjoyed this session and feel a lot smarter as a result. So thank you so much. Well, why don't we wrap it up? Thanks everybody for coming. It's been a great time. Take care now.
Thank you. Cheers. Bye now.
Bye-bye.
Thank you.